So hi everybody. I think everyone knows who I am. So I'm just going to start talking. So I said the title of the talk. It's Statistical Mechanics. Statistical Mechanics and the Touch Polynomial. And although I put it in this order, the title, I'm going to actually start talking about the Touch Polynomial and finish on statistical mechanics just based on the fact that the majority of the audience is math. So just to keep your interest, I guess for a while, and then at the end you can fall asleep with the physics, or if you're a physics person, then you can fall asleep the first half and then wake up for the second half. So let's start with what I said here, the Touch Polynomial. So always G is going to be a finite graph. Where V is a set of vertices, E is a set of edges. So everyone, I think, sort of knows what a graph looks like, but I'll draw one for fun. So here is a picture of a graph, and I allow loops and double edges. So all these things are allowed. So this is an example of a graph. Very nice. So a generic problem in graph theory is how to tell two graphs apart. And this is apart up to isomorphism of graphs. So well, I think it's well known that there's no set answer to this. So there's no definitive answer that if I have two graphs, I can tell them apart by this quantity. So like, if everyone's taken topology, you know that surfaces are classified by their genus. But there's no universal, I'll call it an invariant, which distinguishes graphs, but there is an object which I'll call an invariant, so I'll call it a partial answer. The way to distinguish two graphs, or one way to distinguish two graphs, is to find invariance of the graph. So what is an invariant? Well, an invariant is an object for which, so I'm going to associate, I'll write it like this. So an invariant. To the graph, I associate an object, delta G. This could be a number or a polynomial or a vector or something. And if, well, these two objects are not the same, so G and G prime are not equal in whatever sense of equality they have. So if these were maybe groups associated with these things and they weren't equal, then this implies that the two graphs are not equal. Now, the converse doesn't necessarily hold. So if the two, so note, all right, if delta G is equal to delta G prime, this does not necessarily imply that G and G prime are the same. So we can only distinguish if the objects are different. So a good large class of invariants is sort of a useful thing to have in general. So for surfaces, you don't need a large class of invariants. Only one is needed. For surfaces, all you need is the genus. If anyone knows anything about knot theory, the same sort of problem appears in graph theory. There's no universal distinguishing invariant that tells the difference between two knots. But you can list off all sorts of invariants that will be able to distinguish the two objects in general. So just to list a couple invariants, some examples, and then the one we'll focus on is going to be eventually the title, or half the title of the talk, which is the Touch Polynomial. So a couple examples of invariants. The degree sequence of a graph is an invariant of the graph. So I list all of the degrees of each of the vertices in ascending order. And this is an invariant of graphs. So if two graphs have just different degree sequences, then they're necessarily different. And it doesn't take too much thought to realize that this is true. But of course, if the degree sequences are equal, it doesn't necessarily mean the graphs are equal. So another example, so I'll call this example 1. Example 2, the spectrum of a graph. So graph spectrum. So this is on the spectrum of the graph Laplacian. So this is of delta, which is the degree matrix minus the adjacency matrix. So this is another useful invariant of graphs. I look at the spectrum of this graph, and it's actually an invariant of the graph. So if I change my representation of the graph, the spectrum remains the same, although the graph Laplacian may not. And even the actual spectrum of the graph actually reads off important properties of the graph in addition to actually distinguishing the graph. So for example, the number of zero eigenvalues I'll write dimension of the kernel, is the same as the number of connected components of G. So the last example, and it's a pretty wide class of examples, but I'll just label it as one because eventually we're going to find out that this one is the universal quote unquote invariant. So I can also associate to a graph a polynomial in a seemingly strange way at first, but we'll see that it's at least an invariant. Why is it a useful invariant? We'll also see that because it's easy to compute is going to eventually be the reason. So example 3, I did not describe very well. It's very vague. So we're going to spend a little time kind of breaking apart what I mean associate to a graph of polynomial. So what do I mean by this? So definition of the Touch polynomial. So I'm given a graph G with vertices and edges. I define a polynomial in two variables, delta G of T and S, which is the sum overall. I'll write a subset of G. This is either subgraphs, or we can think of them as subsets of the edges, because you can think a subset of the edges defines a subgraph of the actual graph. And it's defined to be the sum over all subsets of the edges, T minus 1 to the, and there's going to be numbers associated with this, R of E minus R of A, S minus 1, the size of A minus R of A. Subset of E, all right, maybe. So what are all these things? Well, the size of A is just the cardinality. And R of A, and respectively R of E is another subset of edges. It's the whole set of edges. It is the size of the vertex set associated to this subgraph. So consider the graph formed by, well, taking all the vertices that are included in A, and then the actual set of edges, the size of that vertex set. And then what do I want to write next? Minus the number of connected components. Of V. Oops. Okay. And this is the Touch polynomial. So it's seemingly a very nasty looking definition, but it's obviously an invariant. Why? Because I'm actually summing over all the subsets of the edges. And so it doesn't matter what basis, change of basis I make, what redefinition of the edges I make, it's still going to have the same definition. So just as an example, we'll compute this explicitly once and then never again like this. Let's take a particular graph, K3. Which I'll draw like this, and I'll label the edges A, B, and C, and then the vertices are just, well, the endpoints of these things. So all the possible subsets of the edges, I have all subsets of the edges, A, B, C. So these are the terms that are going to go into my sum. ABC is one subset of the edges. What is R of ABC? So I take the cardinality of the vertex set. So the vertex set of this graph is all of the vertices, and there are 3, so that's going to be 3. Minus number of connected components. Well, there's only one connected component of this graph, so minus 1, which is 2. R of AB is another subset of the edges, so I just take this edge and that edge, and it's again connected. So minus 1 here, and the number of vertices is again 3 because I have this vertex and this vertex and this vertex included in the graph. So 3 minus 1 again, which is 2. I have BC and AC, but these are exactly the same as this one, so I'm just going to write times 3 over here. So there's 3 of this type, we'll call it, with 2 edges included. Then I have, subgraphs with 1 edge, like this one. And here there are 2 vertices. And there's still 1 connected component. So this is going to be 1. And again, there are 3 of these. Why? Well, because I can do this for A, but it's exactly the same for B or for C. So the same for B and the same for C. So the same argumentation holds. And then finally, the empty set of edges. So it has, what do I want to write here? I take no edges. There are 3 vertices, and 3. What do I want to say here? 3 vertices minus 3 connected components. A, B, and C are all disconnected, so they're all separate, and so I get 0 here. And there's only one of these. I can only take the empty set once. So the Touch polynomial then is what? So let's write it out just once. K3 of T and S. Let me just go back up, zoom in a little bit so we can see it. Maybe I'll copy the definition down so we can see it again. Copy. Paste. Let's shrink it down a little bit and put it over here. So I need to sum over all the edge subsets with these powers. So for this one, I have T minus 1 to the 2, or so R of E, first of all, is 2. The whole edge subset is 2, because this is E. So T to the 2 minus 2 times S minus 1 to the size of A, which is 3, minus 2. So this comes from A, B, C. Plus 3 times T minus 1 to the what now? So T minus 1 to the 2 minus, or 2 minus 2 again, times S minus 1 to the what? Let me read this off. 2 minus 2, plus 3 times this now comes from AB, plus 3 times T minus 1 to the 2 minus 1, S minus 1 to the 1 minus 1. This comes from just one edge subsets of the vertices, or one edge subsets of the edges. And then finally, plus the last term, which is going to be, what is it? It's going to be T minus 1 to the 2 minus 0 times S minus 1 to the 0 minus 0, which is, after some computation, I'll just write it for you, S plus T squared. So if you didn't follow that computation, don't worry. The point of it was sort of show you just that the computation of the Touch polynomial, at least at this level, is very nasty. It's not so nice. So one would think immediately, why do you care about the Touch polynomial if it's so difficult to compute? Well, one reason is, well, the title of the first half of the talk, that it relates somehow to statistical mechanics. But the second reason is that, let me write a sentence, not so easy to compute, is that there's actually an important relation that the Touch polynomial satisfies, called a deletion contraction relation. And if anyone's ever taken a class on knot theory, they're called Skein relations. So you might recognize them from there. Hold on, let me go back to my, what did I just do? That's fine. Can everyone still see my screen? Hopefully.
Yes.
Okay, good. So Tut now noticed an important relation. It's kind of not quite historical, but for our purposes, it's good enough. So I'm going to make 2 definitions: the deletion of an edge and a contraction of an edge. So deletion E and contraction of E. So given a graph G, if E is an edge in E, I define the graph G minus E. It's a new graph, and it's going to be the graph defined by taking V, the original vertex set, and removing E from the edges. So pictorially speaking, this is easy enough to see. I'll give an example below. So let's take, this is our graph. So this is G. Let's take this as E. And then G minus E is just this. The contraction to be now. So if G is the graph with vertices and edges V and E, E, which is going to be, I'll call it V1, V2, is an E. I define G quotiented by E, or the contraction of E, to be the vertex set modded out by identifying V1 and V2, and removing this edge from the edge set. And again, quotienting appropriately V1 and V2. Looks kind of complicated, but again, pictorially speaking, it's not so bad. So if G is this graph, then G quotiented by E is just I contract this edge to a point. So it will be the graph, this, like a triangle. So I just contract the edge to a point. So why are these two operations important? Well, it turns out that the Tutte polynomial behaves very nicely under contractions and deletions. So here's a nice theorem, which we'll prove if people want to see it, but if they don't want to see it, then I won't prove it. It's sort of a long proof. So if G is a graph with vertices and edges, and E is in the edge set, is not a loop or a bridge. So a loop, of course, I'll draw both. So the blue one is a loop, and this is a bridge. So loops are things that connect the same vertex to themselves, and bridges, if I cut a bridge out, the graph becomes disconnected, or the number of connected components of the bridge or the graph increases by 1. So hence the word bridge. If you cut a bridge, then the things are disconnected. So if G is a graph and E is not a loop or bridge, then the Tutte polynomial, what was I calling it before? The Tutte polynomial of G is the same as the Tutte polynomial of G minus E, plus the Tutte polynomial of G quotiented by E. So this is called the deletion contraction relation. And it makes computation of the Tutte polynomial significantly easier. You can do it essentially pictorially. Why did I make this a different color? Color red. So one may ask before I continue with this exposition, what happens if E is a bridge or a loop? Well, if E is a loop, then there's actually another simple relation. G of S and T is just so loop, I multiply by S minus E, S and T. So I just delete the loop and I multiply by S. So, and finally, I want to fit it on the same page. Maybe I'll just go to the next page and write, or no, I can probably fit it right next to it. If E is a bridge now, what do you think I do in that case? Well, it's going to be similar. Instead of deleting the bridge, I'm going to quotient the bridge. So I just contract the bridge to a point so that now the graph is connected between the two. So it's just one vertex and the graph would look like this in this case. So I quotient the graph by E, and I multiply by T. And this is what happens if it's a bridge. E is a bridge. So this allows us to compute essentially the Tutte polynomial of anything we want. So it's called a deletion contraction relation if you've taken, or if you're familiar with knot theory again, it's what someone might there call a Skein relation. So very similar in form to that. And one of the reasons that the Tutte polynomial is so important is that it's actually the universal object which satisfies such a relation. So any other graph invariant satisfying such a relation can be written in terms of the Tutte polynomial in interchanged variables or fixing one of the variables or so on and so forth. So it's universal in that sense. It is the most general polynomial which satisfies such a relation. So just to show you why this relation is so useful or important. So let's do another example. We're going to do K3 again. So we're going to compute the Tutte polynomial of K3 again. So here is K3. In a bit of an abusive notation, I'm going to write delta of this graph. And we're going to compute this thing by using the deletion contraction relations. So we're going to focus first on this edge here. So by the deletion contraction relation, what can I do? Well, I can either delete this edge, and I get this graph, or I can contract the edge. And I get this graph. So those are the two operations. And by the deletion contraction relation that I wrote before, where did I write it? here. The Tutte Polynomial of, well, K3 is going to be just the sum of the Tutte Polynomials of these two graphs. So now all we have to do is compute the Tutte Polynomials of each of these graphs. Well, how do we do that? Well, we keep applying the same relation. So let's continue in this fashion. This edge here is a bridge. If I delete this edge, then this vertex is disconnected from these two. So this is a bridge. And so if I delete a bridge, or I don't delete a bridge, I contract the bridge and I multiply by t. So here's going to be times t and a contraction. So this is the same as the Tutte Polynomial of this graph times t. And then this one, okay, so if I delete this edge, the graph is still perfectly well defined. It's on a bridge or loop, so I can delete it. And by the deletion contraction relations again, deletion and then contraction. What do I get? Well, this is the same as the Tutte Polynomial of, if I delete, I just get this graph. And if I contract, I get a loop. So what to do for the rest of these? Well, I just compute the remaining Tutte polynomials. So if you want the Tutte polynomial of 1 is defined to be 1, or you can compute it to be 1. And the rest of these are simple operations. So here I contract again. And I end up with t squared times the Tutte polynomial of 1, which I can easily compute to be 1. Here I delete again, or contract again. And I get t times the Tutte polynomial of 1. And here it's a loop, so I multiply by s. And so what I end up with at the end is that the Tutte polynomial of K3 is, well, exactly what I got before. So again, you can easily compute the delta of 1 is 1. And so I get that the Tutte polynomial of K3 is t squared plus t plus s. So, and you can tell just from, just computationally speaking, that this is much faster than running through all of the subgraphs, especially if the graph is a lot more complicated than this. Running through all subgraphs is sort of a difficult thing to do. But running through subsets, or just running this by deleting edges, this is something on the order of the number of edges. This is on the order of number of subgraphs. So computationally speaking, it makes this polynomial much faster to compute. It's still kind of lengthy, but it's at least very procedural. You can do it pictorially. So it's a lot more, I would say there's a lot less room for error in computing this polynomial now. So we'll do one more example of a computation. And then I'll give you some reasons why the Tutte polynomial is important. And then we'll talk about something completely different, which is statistical mechanics. So everyone's following so far. Are there any questions, comments, concerns? If not, then we'll compute the Tutte polynomial of the cyclic graph of order n. So this is the graph that looks like. And there are n things. So if there are no complaints, then we'll continue on. So how to compute the Tutte polynomial of this thing? This is a little bit more general. It's on n vertices. And what do we do? Well, the easiest thing is just to pick an edge and delete it. So if I delete this edge, what happens? Well, I have a big chain of size n minus 1. And well, what do I do with chains? Well, I can delete each of the edges individually. So when I delete this one, it becomes disconnected, so I just multiply by t. And then I delete the next one, I just multiply by t again. It's just by induction, it's just one of size smaller, another chain of one size smaller. And so this chain ends up just being x to the n minus 1. So each, or not x, but s, or t to the n minus 1, sorry. So each link I end up with, I just delete t. So it's going to be t to the n minus 1 plus when I contract. So this comes from deletion and induction. And contraction, what do I get? Well, when I contract this edge, I just have n minus 1 edges in a loop, which is just the cyclic graph of order n minus 1. So plus delta Cn minus 1. So we can sort of compute inductively what this is, as long as I know what t of C1 is. So C1, or sorry, not t, but delta of C1. Sorry, I'm changing notation on you. Is delta of this graph. which is just a loop, which is S. So therefore, by induction, the Touch polynomial of Cn is just t to the n minus 1 plus t to the n minus 2 plus dot, 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 all the way down to t, and then plus S. So there's another nice computation of a Touch polynomial. Fairly succinct. Okay, so this sort of shows you why is it important. Okay, so let me list a couple properties of the Touch polynomial before I move on to something completely different, just to further motivate why it's important, why computing it would be important. So 1, if I evaluate the Touch polynomial at 1, 1, this gives you the number of maximal forests. Maximal forests. Another stupid one, delta G of 2, 2 is just the number of, or it's 2 to the number of edges. So that's another easy one. If I evaluate the Touch polynomial at 1 minus k and 0, this is up to some overall factor which depends on k, which is computable. It's nothing super important. This is just the number of k colorings. What else? Let's do 1, 2. So delta G of 1, 2 is the number of spanning trees. So an easy way to compute all of these things is just to compute the Touch polynomial, which is very procedural, and then you can just read off all of these nice properties that or all of these nice important quantities you would want to compute for the graph to start with. Okay, so any questions on that? That's all I think I'm going to say about just the Touch polynomial. It's now time to move on to what I would call the interesting part of the talk, which is the relation to something physical-ish. If there are no questions, then I'm going to draw a big red bar, maybe 2 big red bars. And now for something completely different. So something completely different. So this is the Ising model. So I want to talk about the Ising model now. What is the Ising model? It's a very simplistic model of a magnet. So I'll write a simplistic model of a magnet. So what am I going to do for this, or build for this model? I'm going to start with a graph. And the graph is going to be considered as my whole magnet. And at each vertex of the graph, I'm going to associate a little tiny magnet, which can either point up or it can point down. So to each vertex in G, I associate a tiny magnet, which points either up or down. So pictorially speaking, here's my graph, and to each vertex, I'm associating a little magnet which points either up or down. And of course, the set of all configurations of these magnets is equivalent to the set of all maps sigma from the vertex set into the set plus or minus 1. You can think that the set of all maps like this are just assigning to each vertex whether or not the magnet points up, which would be +1, or points down, which is -1. So I'm going to call this set something because we're going to use it later. I'm going to call it sigma. So another stipulation we're going to make of this magnet, because otherwise we won't be able to get anywhere, is that the magnet only interacts with little magnets, only interact with their nearest neighbors. So for example, this magnet Actually, well, this magnet actually talks to everything because everything is the nearest neighbor to this one. But this magnet, for example, maybe it's a better example, only will talk to these two. So you can think of this as some notion of short range interaction. So magnets only talk to their nearest neighbors. So again, nearest neighbors, i.e. The magnet at V only talks to magnets connected to V by an edge. Okay, so we have this notion of short range interactions. That's what I'm saying. This is like short range interactions. Okay, so it's a magnet, or it's supposed to be a model of a magnet. So what do I expect of a model of a magnet? Well, I expect that all of the little magnets would want to align, just like a refrigerator magnet would. So I want them all to point in the same direction. So I expect this blue again. I expect that all magnets tend to align, i.e. A lower energy configuration of the magnet has more spins aligned or more magnets aligned.
So there's no external field. Oh, sorry.
It was just really loud on my computer. But for right now, no. We can add one in later, but we want the magnet to align, even with the external field, if there is one, yeah?
Well, if there's an external field, then what you've said makes sense. But how do they have minimum energy if they're all aligned without the presence of an external field?
Okay, well, it takes more energy to hold a magnet pointing this way. I mean, if I have two refrigerator magnets, one's pointing south and I point them north to north. It takes more energy for my hands to hold them together than it does to take them hold them south to north, yeah? For them to point in the same direction.
Mm-hmm.
And that has nothing to do with an external field. It's just the fields coming from the magnets themselves. Correct?
Okay, yeah.
That's the idea. And now if I have an external field, you can think I turn on an external magnetic field on the outside, then all the spins outside almost tend to align with the external magnetic field out here. But again, that's a different story. So let me kind of draw a picture of what I mean by lower energy configuration. So simple example. Let's do this. This configuration, the energy of this I expect to be less than the energy of something like, let's say, if these three are aligned and this one's misaligned. So it takes less energy to hold all the magnets pointing in the same direction than it does to misalign one of them. So this one has higher energy in some sense. And we'll make that a little bit more precise right now. So I'm going to define the energy of a configuration. So given a configuration sigma of the magnet, I define its energy to be what? Where did I put it? To be the sum in interaction strength sigma of x, sigma of y, the sum of all edges in the graph with a minus sign, E of sigma. And I'll say another word about this in a second. So where does this definition come from? So think again back to this definition I gave of nearest neighbors. So spins only interact with their nearest neighbors, or magnets only interact with their nearest neighbors. So only contributions of coming from edges are contributing to the total energy. So if x, y is an edge in E, so let's take this edge. Clearly, this is going to have this and this. I want to have energy. So these two configurations, I want to have energy lower than the misaligned ones. So either this or this. So I can think that the energy coming from that individual edge, maybe E wasn't a good letter. Maybe I'll use like script E or something here, just to differentiate it from the set of edges. So let's do script E or something. I don't know. So the energy coming from an individual bond or edge, so of x, y, should be proportional to something like the product, maybe a proportionality constant times the product of the values of the spin. So if they're both +1 or they're both -1, this number is positive and the overall number is negative, and so the energy is lower. If they're different in sign, then this number is positive, and so the energy is bigger. So that's sort of the motivation for this definition of the energy. The more misaligned the spins are, the higher the energy is, sort of the intuition to have here. And more complicated models of the Ising model. So this is the energy of what's called the Ising model. This whole thing is called the Ising model. And more complicated versions can have different interaction strengths. So J is called the interaction strength, different interaction strengths per edge, where it's going to have constant interaction strength everywhere. And we can also add what's called an external field. It could be constant. It could depend on the site as well. It represents an external magnetic field. For right now, we're going to ignore this for sake of just simplicity. So, right, we want to discuss this. We want to discuss statistical properties of this magnet. Of the magnet, i.e. what is its average energy at a given temperature, or what's its average magnetization at a given temperature, so on and so forth. So I wanted to now assign a probability to a given configuration of the magnet. And a good expectation is that the higher the energy, the less probable the configuration should be. So drawing this, here's E of sigma, P of sigma. So the heuristic I'm going to use is that higher energy configurations have less probable. Are less probable. And the easiest way to achieve this is just to set P of sigma equal to e to the minus beta E of sigma. Beta is some constant that I have control over. So beta is a positive constant. It's not going to be equal to, it's going to be proportional to. So this behaves exactly like what I drew here. So the probability of being in a particular configuration is just proportional to e to the minus beta e to the sigma. And what is the actual proportionality constant? So the proportionality constant is called the partition function. And it is the sum over all the configurations. I did script E, I think, didn't I? Let's stick with that. E to the minus beta E of sigma. So this object is fundamental. So this is called the partition function of the model. And it's fundamental in the sense that essentially any relevant statistical quantity we want to compute is computed in terms of the partition function. So for example, the average energy of the magnet is computed as a derivative of z of beta. The average magnetization, if I include an external field H, we actually get something non-trivial. If it doesn't depend on an external field, then the average magnetization is always going to be 0 by a symmetry argument. But if we do let it depend on an external field, this also depends on H, and it will just be minus dd beta, or ddh now, log z of beta. What's called the free energy of the magnet, which is the energy available to do work of this magnet, is just beta log z of beta, 1 over beta log z of beta, minus 1 over beta. Free energy. So lots of important quantities that we want to compute, statistically speaking, can be computed in terms of this object called the partition function. So you can think, for all intents and purposes, if I know the partition function, I know everything I need to know about this magnet and its statistical properties. So the question is how to compute the partition function in general. And the short answer is to sum over all configurations of the magnet, the energies, which is very computationally intensive because there are order E terms here, number of edges terms here, and there are order 2 to the number of vertices here. So that's a lot of computations that need to be done. So computationally speaking, it's not very fast to compute the partition function in this way. But we can realize that a connection to an important object, the polynomial, which makes computation of this partition function a lot easier. So the answer is that it's directly, it's not so easy. But, and this is where we'll start getting into more interesting things. So we're going to make a change of variables to make things easier. So I'm going to define eta to be the arctangent or hyperbolic tangent of beta j. So using an identity. So here's an identity. So remember that sigma x, sigma y, the product of these two numbers is plus or minus 1. This number here is plus or minus 1. So this is really just either beta j or e to the minus beta j. And well, that makes this actually, I'll write it. No, I can always write it as one thing. I'll write it as cosh beta j plus sigma x, sigma y, sinh beta j, which is the same thing as cosh beta j times 1 plus sigma x, sigma y times eta. So there's a nice identity for us. This is equal to that. And cosh beta j, there's some trig, or not trig, hyperbolic identity, I guess, that gives it, this is a function of eta. It's like what, 1 over square root of 1 minus eta squared, something like that. It doesn't matter so much. We're going to kind of ignore this constant from. But anyways, I can now rewrite the partition function as, so I can rewrite z of beta as, so let's copy it down. Z of beta was here.
What are these symbols again? The you had these left and right arrows.
Left and right arrows are up and down arrows. These ones
Or no, at the bottom of the page, these are like,
expected value. So it means
Oh, okay.
Statistical average. So as a definition, this is the sum over all the configurations, E of sigma, the probability of being in that configuration. And you can check by direct computation, by the definition of the partition function, that if I differentiate z with respect to beta, and then put a minus sign in front, and then divide by z of beta, this is exactly the average energy. So it's a fast way to compute things, essentially. So this means a good point, the statistical average. And in general, if I have a quantity x, its average, so x is a function defined on the states or configurations, say real valued, its average is defined to be x of sigma, p of sigma. Thanks. So continuing on, z of beta is this, which I can now rewrite as the sum over all configurations. The product, so remember that E of sigma, let me copy this over so that you can see what it looks like. So here's E of sigma. It's just the product over edges. Oops. Over all the edges. E to the minus beta j sigma x sigma y, which is well, this thing here. So this becomes the sum over all configurations, the product over all the edges, and using the identity that we just did up here, so I'll call it star, using star. This is 1 plus eta sigma of x sigma of y, and then times, I'll put it out front for right now. I have a product of cosh beta j. This doesn't depend on sigma x or sigma y, so it's just a product over all of the edges. So it's cosh beta j to the size v, which I'm just going to call, it's not super important. So for us, I'm just going to call this whole thing f of eta and forget about it for a while. Again, it's not super relevant. So I can rewrite this a little bit further as f of eta times, and here's something that looks a little bit more complicated, but it will take a moment's thought to realize that it's true. The sum from k equals 0 to the size of the edge set. Eta to the k, the sum over all configurations, the product over edges in E prime, And this is a sum over E prime subset of E, one more sum. Sigma of X, sigma of Y. So where does I just interchange two sums and I actually redid this sum. So I actually evaluated this product a little bit more explicitly. So how did I do it? Well, every time I multiply through, so what is the highest power of eta I can get? It's eta to the size of the edge set. That's if I multiply all of these things together. And then I have a product of all of these edges. So it'll be the product of all edges, eta to the size of the edge set, and then nothing else. What about all but one? So eta to the next power, eta to the one lower power. Well, I'm then missing one of the edges, the one between whatever edge I skipped and the rest. And so that'll be eta to the one less power, eta to the k minus size of E, I guess, minus 1 times the product over all these, over all the edges, besides the one that I skipped. And there are however many I can skip in there. So this is just a rewriting of this sum. It's just an overall evaluation of this product. And then I interchanged the sum over all the edge subsets and the sum over the configurations. So the question I'm going to ask now is pretty straightforward. This quantity here, I claim is 0 very often. And the question is, when is this non-zero? And is it different depending on the configuration, the edge subset, blah, 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 blah. So I claim that it actually only takes two values. And so it actually will end up being very easy to compute. So we'll compute by example, essentially. So let me copy this quantity over to the next page. I'll kind of demonstrate what I mean by it. So it's a product over all edge subsets of sigma x, sigma y, and then I sum over all configurations. So this quantity. So let's take an example graph. I'll do the one that I drew in my notes. Okay, let's take this one. And I'm going to take the edge subset that I'm considering to be, let's add one more edge in. So the edge set that I'm going to consider is this edge, and this edge. So E prime here is this. So this is just one particular example. So the product over all edges of sigma x, sigma y here is going to be, so let's label the vertices just so we can make it a little bit more explicit. I'm going to label this one x, I'm going to label this one y, and this one z. So the product over all the edges of this thing is going to be sigma x times sigma y times sigma z times sigma x. So this contribution comes from, let me label the edges 1, 2, and 3, from 1. This one comes from 2, and this one comes from 3. Now, if I regroup the terms, I'm going to group these two together, sigma y with sigma y, sigma z with sigma z, and then sigma x with sigma x. So notice that, why did I do this grouping? Well, notice that sigma x is either plus or minus 1, so sigma x squared is always plus 1. So the product, independent of the configuration I pick, is always going to be plus 1. So therefore, the sum over all sigma, the product xy and E prime, sigma of x, sigma of y, is just the sum over all configurations 1, which is just 2 to the size of v. 2 to the size of E, which is the same as 2 to the size of the number of vertices. So that's very nice. Does it work out like that always, though, is kind of the question. And the answer is sort of yes. So let's copy this down again. So this was example 1. Let's do example 2. So let me draw the same graph. Looks like a fish, and then it has this thing and this thing. So I'm going to label the edges again. I'm going to label, so the edge subset I'm going to pick this time is going to be this edge, and this edge. I'm going to label them 1, 2, 3, and I'll label the vertices x, y, z, w. So let me just copy this down so we know what we're computing. Copy, paste. So let's see, the product over all the edges now. And this edge subset, so this is our E prime in this case, the red, over x, y, and E prime is going to be what? What's going to be sigma x times sigma y sigma y times sigma z, and then sigma z times sigma w. So again, this comes from 1, this comes from 2, this comes from 3, and I can regroup again partially. So this groups with this, and this groups with this. So both of these are 1, but what I'm left with at the end is going to be sigma x times sigma of w. So then this sum overall sigma is going to be the sum overall sigma of x times sigma of w, which is the same as if I sum, and how did I write this? Sigma in sigma prime. Sigma prime now is I take the vertex set and I delete, let's say, the edge x. So sigma prime is this all maps from this set into plus minus 1. Essentially, I'm just showing you that this sum always has odd parity. So sigma of w minus some sigma in sigma prime, sigma of w. So this comes from all of the elements of sigma which have sigma of x is plus 1, and this comes from all the elements of sigma which have sigma is minus 1. So I get overall 0. Sum is plus minus 1, plus minus 1, plus minus 1, and essentially all I'm saying is that the pluses and minuses all cancel out, so I get 0. So what was the difference between this example and this one? Well, the difference was that some of the vertices here had odd degree, whereas here they all had even degree. And I need them all to have even degree for the sum to not vanish, because what made the sum vanish here? What was the fact that if I have anything left over at the end, I can break the sum into 2 pieces, the part where this is 1 and the part where this is minus 1, and I can cancel things, and then I get 0. So this part comes from sigma of x equal to plus 1, this part comes from sigma of x equal to minus 1. So overall I get 0. So the contributions, closed loops I'll call them. This is what a physicist might call them. I'll give a better name in a second. Contribute. I.e. subgraphs of G with every vertex having even degree. In other words, they're called Eulerian graphs. So actually what I just found is the partition function counts something for me. So z of eta is this function f tilde of eta, or f of eta, I think I called it. Okay, a factor of 2 to the size of the vertex set coming from this thing here. It's the same on anything with closed loops, times the sum k equals 0 to the size of e, ck a to the k. And what are these constants ck? So ck is just the number of Eulerian graphs with of size k, I guess, in G. So with k edges in G. So very nice. I can actually compute explicitly what this thing is, and it's very graph-theoretic looking. It has all of these coefficients which depend on something, well, extremely graph-theoretic, the number of Eulerian graphs of size k in G. So how is this related to the Touch polynomial? Well, it turns out that this object is closely related to something called the chromatic polynomial, and it's actually a reduction of the general Touch polynomial I wrote earlier. So I'm going to, because we're short on time, just write the generalization and I'll kind of tell you how things work. So I'll write a sentence. Z itself is a graph invariant, which is pretty obvious from the definition or the final formula we came up with at the end. Variant. And a generalization of this model is called the Q-POTS model. And it's exactly the same thing as we did before, except for I take now my configurations on the graph. I take magnets which are allowed to point in Q different directions instead of just up and down, you can think. Q is in Z plus and bigger than 2. So it's a generalization of the model we had before. I just shift everything up by 1, you can think. I again take the Boltzmann distribution on this model, Boltzmann distribution. That is to say, the probability of being a particular configuration is proportional to e to the minus beta e of sigma, or e of sigma here is again very similar to what I had before. It's sum over all edges, so I have only nearest neighbor interactions again. And it's 1 if sigma x is equal to sigma y, and 0 otherwise. So equals 1 if sigma x equals sigma y, 0 otherwise. And I can again write the partition function. So the partition function for this model for the Q-POTS model actually has a very simple form. It depends on eta and it depends on Q. So eta again is exactly what I defined before. Eta is this cosh of beta j. And it's up to another factor, just like I had before, like 2 to the v, e to the something that depends only on eta. And is independent of the graph chosen. Sum over all edge subsets. Q to the k of e prime. Eta to the size of e prime. So k of e prime is the number of connected components of the graph with vertices and then edges e prime. So a very simple change of variables. So if I set t to be 1 plus q over eta and s to be 1 plus eta, s equals 1 plus eta, sorry. Z of these new variables, t and s, is exactly the same thing as the Touch polynomial. So there is the variance of the Touch polynomial as promised. It comes from a slightly more general model than the Ising model, but it's just a little bit cleaner to describe what happens for the Ising model. And just because I'm short on time, I'm going to kind of stop there. There's maybe the last comment. So this gives a nice connection of, well, the Touch polynomial to something, well, that came straight from statistical mechanics, which is the Ising model / the Potts model. There are lots of reasons that these models are important in statistical mechanics. One is that they're very simplistic models of what's called a phase transition. They're essentially the simplest models you can come across, which exhibit a phase transition. And the large size limit of these things is very important. To actually show the existence of a phase transition, you need an expansion of the partition function like this to actually predict whether or not a phase transition exists. So this is one reason that it's so important. It's also important for reasons of, well, computational complexity of actually computing this partition function and so-called solving the Ising model. We saw that there's a very nice algorithm for computing the Touch polynomial. And so that implies that there's a very nice algorithm for computing z. And, well, conversely, we had this very nice way of computing z using these pictures. And so we can, well, read that back and say, now there's another way to compute the Touch polynomial. So there's a couple more specifications, like if G is planar, there's actually an even better way to compute this. It's called Fisher-Castellan temporally algorithm, FKT algorithm, which allows you to compute it essentially however fast you can compute determinant. It's that fast. But maybe for now, I'll stop just to not bore you. So any questions? That's all I really have to say. Thanks.
Wow,
So,
they really
okay.
don't like physics, huh?
Oh, I don't know. So there's also maybe I'll say one more thing. Well, I have you all cut. There are lots of other interesting directions to take with this sort of thing. So you can also introduce, like I was saying before, an external field and do all the same computations. And what you get is not quite a Touch polynomial anymore, but it's like a generalization of the Touch polynomial in non-commutative variables, something like that, if anyone is interested in hearing. So that's very interesting as well. If you include the external field, you get interesting generalization of the Touch polynomial, which doesn't obey deletion contraction relations anymore. So you kind of lose this computational ease of the model. But it's interesting that it's more general, I guess. I don't know. There's also interesting computing, well, the same model, but on random backgrounds. So I sum over all graphs now and ask similar questions. And well, there are different techniques entirely involved, but it's also something interesting. Question from someone, or is that just background noise?
I had a question actually.
Sure.
So this recurrence type of formula with the contraction and the deletion that you showed for the Tutte polynomial,
Right.
that should lead to a polynomial time algorithm, if I'm understanding right?
I think so. Yeah, I think you're correct. It should be what order of the number of edges in it, right? Something like that. It's linear though, I think. You're right. Or is it linear? I don't actually know. Probably you're computer science, so maybe you know better than I do.
I mean,
My
it
interest-
makes polynomial,
but definitely polynomial, I think, yeah. My interest isn't so much in computational complexity of these things. It's more of the, for me, I actually only need the first few terms of these expansions. So just knowing that such a relation exists is enough for me.
okay.
And I can compute the first few terms. But probably right. As computationally speaking, it's useful. And maybe you know more about this FKT algorithm. So if the graph is planar, it turns out that there's a representation of this partition function, or equivalent to the Touch polynomial, in terms of a Pfaffian, or essentially a determinant. There's a determinant formula for it. So you can compute it. You can compute the polynomial in as fast of a time as you can compute the determinant. And there's the explicit algorithm for doing this. This is due to those people I listed before. I don't know if I wrote their names. Fisher, Castellan, and Temperley. So computationally speaking, that's another, I guess, advantage of this spiel, if you want to call it that.
All right, thanks.
Yeah, sure. Any other questions? If not, oh, okay.
So right at the end there, so you've drawn an equivalence between the partition function and the Tutte polynomial?
Right. A partition function of the Potts model and the Tutte polynomial. So in these
Right,
scaled variables, where are they at? These ones? Oh shit. In these scaled variables, the Tutte polynomial is exactly the same as the partition function.
So what about for like, and not that I have one off the top of my head, but is it necessarily useful to try and compute well, I guess, is this true in all scenarios? Like if I have a different system and I want to describe the partition function for this other system, does it make sense to have a Tutte polynomial for everything? Or
if it's not the one of these lattice models that I've described, which is the either the Ising model or the Potts model, then there's no connection to the Tutte polynomial necessarily. Now, that's not to say there's no relation at all to any graph-theoretic object. It depends on the model, essentially, is what the short answer is. So this is specific to the Potts model. For more general formulas like this, if you're interested in looking, there's a very nice book by, what is his name? Baxter.
Corey Baxter?
No, Baxter. I think it's R. Baxter. It's called Exactly Solved Models in Statistical Mechanics. So most of the models he talks about in there are two-dimensional. One generalization or one example that is not is this one. But most of the models he discusses in this book are two-dimensional, and there is a reason for that, which is a lot deeper and not exactly connected to all of this, but or not exactly connected to what I talked about. But it gives a bunch of examples of kind of formulas like this, if you want.
All right, so is it most obviously applicable only to self-interacting lattice systems?
Well, it's specific to the Ising model with constant interactions and no external field, or the Potts model with constant interactions and no external field. Which I mean, itself is very interesting. I mean, it's the non-trivial model itself, but it's specific to those models. So that's something that should be taken into account. Does that answer your question, sort of?
Yeah. It's crazy that there's even a connection to begin with, if you ask me, but.
Sure. I think most of these results originally were Castellan's, but other people have contributed along the way. So the connection of this model, it's not exactly the Potts model that was the original connection. He has this model called, what is it called? I forget, but there's a different model that Castellan originally considered, and he developed this whole kind of theory for it, computational classes for it, or computational complexity classes for computation of well, the partition function, given that it's planar, and most of his work was that. I don't think he's still alive, but it's he has a lot of interesting work if you're interested. It's results along these lines, I guess. So yeah. Any other questions? If not, let's thank our speaker one more time. And I'm going to stop the recording.